Hello everyone, and welcome to the 9th part of this MOOC dedicated to hydrocracking. In the first part, the role of the hydrocracker was recalled and we spoke about the feed characteristics. Then we detailed the chemical reactions, the associated yields, and the process. Let's now focus on the operating variables of the process. But before talking about the operating variables, if you remember well, we had injected about 4.5 tons per hour of hydrogen, and we consumed 2.7 weight% compared to the feed, or 4.05 tons per hour of pure hydrogen. So we have about 450 kilograms per hour of extra hydrogen that has to leave the reaction section. But in fact, about 250 kilograms per hour of hydrogen will solubilize in the liquid of the HP drum. So there will be 200 kilograms per hour of hydrogen that needs to be purged. And now let's go back to the operating variables. The first parameter is the hydrogen partial pressure. The higher the pressure, the more cracking reactions, and reactions in the pretreatment section are promoted. In our specific case, we look at the pressure at the outlet of the reactor, here about 150 bar, and we look at the volume fraction of hydrogen in the gas phase, here about 87 volume%. This logically makes a hydrogen partial pressure of 130 bars. The second parameter is the amount of hydrogen that is recycled to the reaction section with the recycled gas compressor. In video number 4, we said that a recycled flow rate of 18 tons per hour was considered. And remember that about 4.05 tons per hour of hydrogen are consumed for pretreatment and cracking reactions. We can therefore easily see that we have recycled the equivalent of 3 to 4 times the chemical consumption of hydrogen with this recycle. This ratio ensures a large excess of hydrogen and makes sure that there is never a lack of hydrogen in the reactors. Then we have the residence time on the catalysts. This residence time is typically calculated by dividing the amount of catalyst in cubic meter by the liquid feed rate at 15 degrees C in cubic meters per hour. Here is typical order of magnitude. The amount of catalyst is about 1.5 times the hourly liquid feed flow rate. So, in our case, for 150 tons per hour, or about 150 cubic meters an hour, we will have a total amount of catalyst, pretreatment plus cracking, of about 230 cubic meters of catalyst. Finally, the last main parameter is the temperature in the reactors. And when we talk about temperature, we are talking about an average temperature representative of the catalytic beds. In fact, remember that the reactions are exothermic. The higher the temperature, the greater the severity and therefore the cracking. But be careful, however, not to increase it too much. Otherwise, this would accelerate the deactivation of the catalyst, a sign of having to change it more frequently. If we summarize, the performance of the reaction section of a hydrocracker is dependent on parameters just mentioned, namely the hydrogen partial pressure, the amount of hydrogen recycled, the residence time on the catalysts, and the average temperature. And of course, the type of catalyst that, depending on its formulation, leads to a maximum distillate or maximum light molecule yield structure, or in between. Finally, remember that the catalyst deactivates over time, whether by poisoning by metals for the first beds of hydrodemetallation catalyst, or also by coke formation, as in diesel hydrotreatments. To compensate for this loss in activity over time, an increase in temperature is used as the cycle goes on. After a certain time, we reach a maximum temperature value, whether it is the maximum acceptable by the metallurgy of the reactor, or we crack too much. And we must stop to change the catalysts. The cycle length is quite variable from one hydrocracker to another and can vary from 1 to 2 years depending on the catalytic volume, the treated feed, and the operating parameters. Note that there is therefore an operating window in temperature between the beginning of the cycle and the end of the cycle. The case that has been described here with the temperature at the reactor outlet of 420 degrees C is representative of an end of a cycle. Indeed, for a start of a cycle, one would have a lower temperature of about 400 degrees C. Thus, we can say that we have a temperature range of 400 to 420 degrees C, or an operating window over the entire cycle of 20 degrees C. And if we say that we deactivate at 1 degree per month, the resulting cycle length will logically be close to 20 months. Now that we have recovered our cracked molecules, it is time to split this liquid effluent into gasoline, kerosene, and diesel fuel. So, see you in the 10th part of this MOOC dedicated to hydrocracking. In the meantime, do not hesitate to test your knowledge by answering the quiz and subscribe to my YouTube channel. Refining is very exciting. See you very soon. Bye bye!